Good afternoon to all of you, and now we will talk on uh, snow and glacial runoff modeling. See, this is there are various options to do snow and glacier melt modeling, and in these days there are a lot of uh, high quality, uh, you know. Softwares are available by which by using that you can do the snow and glacier melt runoff modeling. Uh, there are numerous models which you can see, and these are commonly used. However, many of these models are not suitable for snow and glacier melt, essentially because they are used, they represent better this rainfall, runoff models, infiltration, and other processes, evapotranspiration, and so many other processes are quite well represented in that. But snow and glacier melt is not properly represented. But whichever model you want to use in future, it is important for you to understand what is the scientific principles used behind these models. Therefore, this lecture will give you about the fundamental understanding about snow and glacier melt is done. So there are numerous models, and one of the earliest model and where you can have it is the first approximation is you just get the drainage area and precipitation, and then estimate the uh, stream runoff. So you can you can plot relationship between the flow and actual and computed stream runoff by using basin characteristics. So uh, it is uh, it is first of simple thing is to identify how much is runoff possible if you take a basin, then measure the stream runoff, estimate stream runoff per unit area, and then correlated with the geographical area of the basin. You can extend it, like in this particular case where computed 25 years cubic feet and actual and computed by using this basin characteristic. So this is one of the simplest method to do that, and this is the first approximation which was done. But when it comes to the application to snow and glacier, will it work or not? That is very important question. Essentially because there is no one-to-one correspondence between the precipitation and runoff. So if you look this into the Parvati Basin in Himachal Pradesh, you can see that this is a blue is runoff and red is a precipitation. So you can see in the period of winter, that is January, February, and March, you have high precipitation and you have relatively low stream runoff. Um, so, uh, and you can see that even though, and then and subsequently, for some time, there is a very low precipitation, but you have relatively high runoff. And of course, when it comes to monsoon time, you have high precipitation and high runoff. So there is no one-to-one correspondence between the precipitation and runoff. Therefore, we need to look this issue in a very differently than the conventional models of estimation of precipitation and runoff. Um, so, having said that, generally, snow and glacier runoff models will have two principles or two different aspect. One aspect is the estimation of meltwater. That means for a given temperature precipitation and its various other parameters, what is the melt it can produce. Then there are different drainage processes will take over it. That means some of that melt water will drain through the snowpack. It will drain through the soil, and on the surface it will run off, and then it will come as the runoff eventually. And in between, you have to have a principle of conservation of mass. That means the amount of snow available for melt cannot exceed the runoff. So that kind of conservation of mass has to be included into it. So this is the general idea of snow and glacial melt runoff. So we will try to develop, understand some of these ideas behind it, and say, like, let us take the first aspect, and the aspect which is related to estimation of snow and glacial melt. There is the relationship is very fundamental in nature, and we already know that relation. The energy balance equation we really know, where melt is equal to Qm is the energy flux available for melt, and how much energy available for that melt. D is the density of water, HF is the latent heat of fusion, and B is the thermal quality or the fraction of ice in unit mass of wet snow. If we have this relationship can be used to estimate the snow melt, but under normal melt condition, M, because we already know the density of water, we know the latent heat of fusion. So what indeed we need is a Qm, which is the amount of energy flux available for melt, and B, which is the thermal quality, that means how much is the fraction of ice in unit mass of wet snow. Remember, the wet snow will have water as well as it will have ice crystals. Therefore, how much is that fraction is important to know the melt. So that is the idea. So it appears to be very simple to do that. And then the next step is how much is energy, Qm, is required, energy flux available for melt, where Qsn is the shortwave radiation flux available absorbed by the snow. We were talking about albedos and other aspects previously. So you can club this incoming solar radiation from sun into two parts, is the short wave radiation and long wave radiation. So the short wave radiation is how much it is absorbed by snow. Then long wave radiation flux at snow and ice interface. QH is the sensible heat flux, QU is the latent heat flux, and the flux from ground, that means certain amount of energy will transfer from ground to snow. And then there is a rain, that means rain water. That means if really what happens is that if during the melt period, if there is a rain on snow, then certain amount of energy will transfer either to freeze that water, that means to exothermic reaction will take place, and it will lead to the additional melting of snow. And then the change of the internal energy, what it means is that if entire snowpack is not at 0 degrees Celsius, and if it is, it really at night it is very cold, and a certain portion of snowpack changes its temperature, which is much below the 0 degrees Celsius, then initial melting will be used to bring that snowpack at the 0 degrees Celsius. So there is a certain amount of internal change of energy will also take place. That also you have to account for. However, it is generally very difficult to get this all equations solved, energy fluxes, because of the lack of data. So generally this model is not used, but in these days many people are using it, essentially because advancement into the satellite remote sensing and you can also, some of those can be sold and got it. We can do it, but generally we use the temperature index method. So, so normally in operational model, temperature index is used, where the degree days are determined by using maximum and minimum temperature. Remember one thing, temperature is a easily obtainable parameter, and most of the places temperature is available. So you have a maximum and minimum temperature. So if T minimum is less than 0, then it is considered as 0. So why is that? Is that T minimum is less than 0, then T minimum is 0? That is essentially because if we have a large variation in temperature between day and night, so it will cancel with each other and you may not produce any melt. However, the higher temperature in daytime will lead to certain amount of melt, and because of that, this approximation is done. And this is very useful approximation. T is widely observed parameter and good to, and can be made, estimates can be made for various altitude zones. So how do you, so if you look into this parameter, when you want to do this melt, where M is equal to melt factor and divided by T, because M is proportional to T, and therefore you require a melt factor to get the amount of melt which is, so there are different ways by which you can give them estimate the melt factor, and which is one of the ways is a major factor is a proportionality constant. Then Kv is the vegetation transmission coefficient for radiation. Kv Ra is the radiation, solar radiation index, and A is the albedo. So if you know that incoming solar radiation, if you know the albedo, and if you know the vegetation transmission coefficient, and then you can make MF can be, by using proportionality constant, you can estimate the melt. So you can see here how albedo keeps on changing on the snowpack. So this is where a little bit avalanche snow, but this is a pristine snow. You can see little bit change albedo. Albedo can significantly change if there is a contamination on it, and this particular case contamination is a volcanic ash. Albedo can be different depending upon if it is following on the vegetation. So this is albedo will change, as well as vegetation transmission index will also change depending upon the density of vegetation. So all these parameters needs to be included, and then it is important to understand how incoming solar radiation is going to influence because of the terrain. This is incoming solar radiation. You can see here, this is a direct solar radiation, and this is a terrain azimuth angle. So what really happens is, it depends upon the orientation and slope. You can determine how much incoming solar radiation is coming. So you can say that if terrain slope is a 0 degree, that means it is perfectly horizontal surface, then this is the amount of incoming solar radiation you can see. It is, there is no change in incoming solar radiation. You can see this is a line which is going here. So something around 40 microwatt per centimeter square per micrometer per steradian energy is going to come in. So you can see it is there. Now question is, if it is sloping by a 10 degrees Celsius, okay, and it is sloping by 10 degrees Celsius, and it is not necessarily sloping in one direction. So it can be 0, means it can be perfectly north, or it can be, as we move towards the east, then it can change 50 degree from north, 100 degree from north, 150, 200 degree from north, 250 and 300, and finally again at north. So you can see how incoming solar, moment you change the 10 degrees Celsius, you can see that how incoming solar radiation is changing. And when it becomes 150, 160 something, or maybe around 108, so when it is a southern facing, then it gets the maximum solar radiation. And when it is northern facing, it is going a very lowest solar radiation. At this end, it is going. But as you keep on increasing the slope, the incoming solar radiation fluctuations is also dramatically changing. So suppose you take almost 90 degree as the slope. If you take this as a 90 degree of slope, then you can see that initially, if it is a slope towards the north, then it is not receiving any direct solar radiation. That means it is in mountain shadow. So you can see that this remains in mountain shadow if it is a 90 degree slope north until it comes to the almost 60-70 degree from north. And then you can see that as you move up, then it's changing, it is going up to 45, then it is coming down, again it is coming under the mountain shadow. So it is quite possible that, and sometime if you take the slope which is 50 degree, you can see the incoming solar radiation in southern slope will be much more higher than really on horizontal plane. So incoming solar radiation is definitely going to change depending upon solar zenith angle and depending upon the terrain slope. Therefore, it is important for us to understand when you are going to apply this solar radiation index, you need to consider into it the slope and aspect of that. So what is in addition to that, if you really look into the temperature, particularly in Himalayan terrain, the temperature will change with altitude. We already know that if we are in low altitude, the temperature is relatively high, and as you move into the altitude, then temperature is significantly reduced. So altitude adjustment of temperature is necessary. There it is generally temperature lapse rate are used, and the mean elevation of station and mean elevation of area about which you are talking. So you will do that exercise sometime later on today to understand this, and then you can so what it is giving is a temperature index at altitude and temperature index at meteorological station. So TA is the temperature index at altitude, T plus TH. So TA is a negative, then considered as 0 in model, and this will give melt over unit area. Remember one thing, this is not going to give melt over entire geographical region, so you need to convert it into the larger geographical area. The key question is, now once we have a melt parameter which is related to the temperature, then we need to estimate how much is the snow and glacier melt. So how to estimate total melt in a basin? So how much is the basin area in each altitude zone? So first you need to do is take the digital elevation model, plot it put it on the basin area, then have a layer of snow cover on it, and then estimate the ensure that it is on geographical area you estimate each altitude. But it is important because as temperature keep on increasing, it will start producing more and more melt. So how we can ensure that amount of melt water produced is not more than total water stored in each altitude zone. So that is where the water balance come into the picture. That means you require the concept. You have geographical area under snow cover in each altitude zone. You should also require the depth of snow in that area, so you will get the volume of snow available in it. Now you cannot produce the melt which is higher than volume available for the melt. Otherwise, you will be completely off, and that is how you balance it out and do the water balancing into the model. Remember, we are now developing a model which can be used for practical purposes. In order to estimate the snow cover, if you want to do, we have looked into this aspect much more detail in my previous lecture, where NDSI, where reflectance of band 2 and reflectance of band 5 is used to measure the normalized difference snow index, and it can be used to estimate the snow cover. Now, quick question is how to estimate the distribution of snow in altitude zone. So first thing you need to do is estimate the basin hypsometry. What it means is you plot the area versus elevation graph. So you have a this is a Baspa basin hypsometry, which is a Baspa basin is in Himachal Pradesh, and you can see that how area, snow cover area, how total geographical area is varying in each altitude zone. So you take the 2,300 to 800, this 500 meter is this this much area. So each altitude zone, by using this, you get the total geographical area in that, and then you calculate estimation of snow in a different altitude zone. So this NDSI, you run the model on this and get how much is geographical area in each altitude zone. Key question about which we were talking about, how to ensure that amount of meltwater is not more than total water stored. There could be multiple solutions to this problem. If we are having snowfall data, then we can force model and ensure that runoff is not generated more than water equivalent of the region. So I was talking about it. If there are different ways by which you might have observatory there, and then you can estimate how much is the snowfall in that region. If you have snowfall data at different altitudes, then you can develop a relationship between the change in rainfall from one altitude to another altitude, and then use into the model. So you can force it by that. So if each, you know that 10 centimeter is a rainfall, 100 square kilometer is area, you can multiply by it and you will know how much is water equivalent. So you are not going to generate water more than that in that altitude zone. However, it is many times difficult to have this data. So can we use depletion curve to estimate the amount of water stored into the basin? Or in each altitude zone, this work done much 80s and 90s to understand, because there was not enough data available. So you can see here that this is a snow cover in various altitude zones. So you take either 2000, this is in Beas Basin, and this is in March to July, this plot. And you can see that this is a snow depletion curve, or how snow is changing with time from 15 March onward to 15th May, and this is how it is changing. So if you look into 2,400 to 3,000 meters, you can see most of the snow is melting from 15 March onwards, and by middle of May, this is completely over. But if you look into 3,000 to 600 meters, then there is no melt is taking place. It is only after the middle of April melt has started to happen. So if you take this region, which is the 15 March till the middle of April, most of the water which is coming from altitude which is lower. So by using this model, this concept many times for large basins where there is no data is available. We can assess if we have this data for 10 years, 15 years, 20 years, then we can assess how much is the glacier, potentially glacier store water in each altitude zone and do it balancing. But we can do much more than a decent job than this in these days, essentially because we have a lot of satellite data. Now there is sounding data available by which you can get reasonably better estimate of the snowfall also. So you can do in that fashion as well. Now, there's another model which people historically have used, and you should be aware of this, is snow melt runoff model, which is called SRM. So what is this model uses degree day approach. So this was very commonly used in 90s and a couple of decades after that. And this model uses degree day approach and snow cover extent. Model parameters are temperature, snowfall, and snow cover area. For seasonal runoff model uses the depletion curve, and depletion curve and runoff are used to assess the snow reserve for seasonal runoff. Such models are difficult to use for glaciated region which show no large depletion due to runoff. So if you have understand this concept, the concept in this model is, as you see into the previous slide, you require the depletion of snow. That means snow area has to be reduced, and then it is used to water balancing or to estimate the amount of runoff which is going to come from that. However, if you look into the glaciated area, glaciated area is not seasonally going to change that much. That means it's very marginal. If at all glacial retreat going to take place, it is only marginal retreat will take place in a year, not significant as compared to the what snow is going to take place, because we know almost 80% to 10% snow cover will change in a one winter, and in a Hindu-Kush Himalaya region, and in glaciers there is no change in area. So therefore this concept is difficult to apply, and therefore a simple model was developed, and you will work on this model because even though there are better sophisticated models are available, but underlying principle of all those models will be same, and it will give you first-hand information, first-hand information what it does inside the model. So it is not as a black box for you, but you will understand the modeling techniques by doing it on a simple calculator. So let us understand what was the problem which was posed to us in mid-90s or end of mid-90s is Himalaya has a large number of snow and glaciated streams. Systematic assessment of hydropower potential of each stream is needed. So mountain stream has a lean discharge in winter, and the feasibility of hydropower plant depends on winter discharge. So develop a model which can assess the inter-seasonal variability. That was the problem given to us. This may not in these days by considering so much opposition of people for hydropower potential, but that was not the situation in mid-90s where everybody thought that hydropower generation is the ideal thing for the proper development of the mountainous terrain. So this was the problem which was given. So idea was there are a couple of other problems in this. Another problem in this is Himachal Pradesh is a surplus state for power generation, and summer power generated from hydel station can be sold to adjacent state. However, power purchase agreement needs to be done in February. Can we forecast the variability in power generation from previous year? That is another problem which we need to work on, that we have because the power utilities has to make power purchase agreement in February. So they don't know how much power they will generate in a melt season, because February is a snow accumulation season, and the March, April, May, June, before arrival of monsoon, how much power, which is a peak summer season in North India. So can we do it by using how much is precipitation has taken place in that region, how much is the snowfall? Can we say that how it will be different than previous years? So that was the issue on which we wanted to work. And in addition to that, there is another problem. Is Himachal Pradesh, many micro and mini hydel projects are generating power, and many are under planning. Runoff of this stream depends upon snowfield and glacier. How climatic variations can change the glaciers and snowfield, and how these changes will affect future stream runoff and future power generation. So these are the key issues on which we thought we will work, and for that you see way back in 2002, the seasonal snow and glacier melt runoff model was developed, and we will look into that model and see that how it is can be used. So the first model is about the idea is you need to set up the model. What it means is how much is the Q. Q is the average seasonal runoff. Then it has T, which is average seasonal degree day. G is the snow and glacier area. So overall, this model has two specific components. One component is about how much is water generated by snow and glacier, and how much it is generated by land which is not covered by snow and glacier. So that was the idea. So it has three different modules. One model is autumn, winter, summer, and monsoon. But this model starts because snow accumulation season starts. So initially the model starts running from the winter, then for summer, monsoon, and eventually for the autumn. So first thing you need to know is what is the period of a season, because what is summer, monsoon, autumn, and winter. So you can see here the original this model was developed for Parvati River Basin in Himachal Pradesh. So you can see there are summer, the dates are given. However, the dates will change if you go into the very high altitude Himalayas, or you cross the Pir Panjal range, or if you go to the Karakoram mountain range, these dates are likely to change. So, there is a definitely scope to relook into the period of various season. But this was the season was fixed depending upon the hydrograph. That means when snow melt starts, when the hydrograph is changing, when suddenly hydrograph is going up because of the monsoon precipitation, when hydrograph reduces, once monsoon is retreated, and when it is snow accumulation starts, when it reaches to the base flow, how minimum stream runoff is. So basically by using hydrograph, it is grouped into 1, 2, 3, 4 seasons into the Himalaya. So you take the daily rainfall data, which is available at that time, very old data, subsequently 90 to 95. The average winter snowfall was available 20 stations for 1970 to 1988, and it was used into the model. So there are different melt factors are given. It depends upon if you have gone into the field and collected data to estimate the melt factor, it is fine. But most of the region it might not be available. Therefore, you get the simple relationship is density divided by density of snow, density of water multiplied by 1.1, and you get the melt factor. So melt factor is a parameter which can be tuned into the model. And yeah, is there any problem with that, Arya?
No, sir, it is visible only. Slide is visible.
Fine.
Yeah, it's fine.
Something went wrong. Hold on.
Okay.
Is it
It is
working?
Yes, sir, it
Huh?
is working. Yeah, slide is visible. That melt factor slide.
Okay.
That
So
table. Yeah.
it is giving you message that hold on, you are, So what is, so these are the melt factors you can use. And then there is IG of runoff coefficient. What it means is, it is as you as you produce the amount of water by snow melt, it is not necessary that all melt water will go into the stream runoff. Some of that will be abstracted by the land. Some of that will go infiltrate into the ground, and there might be evaporation or evapotranspiration. So there is a different runoff coefficient, but predominantly runoff coefficient are 0.6, 0.7, and 0.8. So it depends upon, say, glacier melt in summer has slightly less runoff coefficient, and then the seasonal snow in summer has a high runoff coefficient. Snow and glacier melt in winter has little bit less runoff coefficient, because some of the energy or water will be used for internal consumptions by snowpack, and monsoon precipitation is very high, and autumn is very high because the soil is at field capacity and making it run off. It's very efficient. So these are the ideas were put into it, and you can give the runoff coefficient. So what was done in this case is, originally this is a Beas basin, this is a Bhuntar, here is a Kulu and Manali somewhere here, and this is a one Malana Nala where this model was developed. Then this was tested at Taushnala, and then it was handed over to the Himachal Pradesh Electricity Board, and they independently validated at Soramgarh, where a lot of runoff data is available, and finally it was extended for Vangargarh and Kirangarh, and after that we just installed the program on electricity boards, computers, and we have really withdrawn from this activity. So you will actually do this activity by yourself. I think subsequently after my talk, you will have exercise on this, and you can see here how Malana Nala's accuracy, like autumn, winter, summer, and monsoon, it is varying from 2 to 10%, but monsoon is very off, essentially because they are not thermally controlled. So the model is thermally controlled, and it is not really producing good result in monsoon. And you can see that Taushnala, how errors are there. Errors, sometimes it is better, but it is still worst in monsoon. And same thing is Runoff and Kirangarh. You can see how it is varying. So you will do this exercise on your own in subsequently, and you can also estimate the power potential in megawatt. You can see that autumn, how much is runoff, how much is the field runoff model, and power potential, how much is this is unrestricted power potential. So you can see how power potential is changing. Winter it has lowest as 15 megawatt, and it is autumn is almost 40 megawatts, summer is slightly higher, and monsoon is very large. So monsoon is not a problem. So idea is, what should be the ideal power plant which can generate power so that it remains as economical, whether it wants to take benefit of high monsoon precipitation and keep plant idle for very long period, or they want to go for mean and allow monsoons runoff to go through it. So this is how this work was done, and I think here I will just say that how things are moved from there to a very different level in these days, where you can do it by using very sophisticated models like WEEP model, where temperature, precipitation, land and soil depth, glacier depth, humidity, hydropower it can be used to estimate. You can estimate the runoff, and you can use it to hydropower generation. But remember one thing: understand the fundamental aspect. Even if this model is sophisticated. As far as snow and glacier melt is concerned, the same. So you may not understand it, but you can use the sophisticated model to do it, and you can get all kinds of data like a DM from Aster, Mori snow cover area, cloud mass, land cover. You can get wind speed, relative humidity, then soil databases, historical data you can say, and climate projections also you can get. So now you can use these models to estimate how stream runoff is going to change in future, and a different time frame using different atmospheric model. That means RCP 4.5, how it will change the stream runoff from 2050 to 2090, or RCP 8.5 from 2050 to 2090. So all these things are now possible, but it is only possible for you if you understand the underlying scientific principle which is used in these models. So some of these models are using um, uh, temperature index. There are some other models which I am talking about. There are other models which are using the energy balance also. So, but underlying principle is same, and it is important for us to understand the basic idea behind the model. With this, I think I will stop here and take some questions.